All right, hi everybody. My name is Ayaz, and today I want to tell you a little fun debugging story about memory leaks. So some time ago, I developed this piece of software. It's called ABQ. The idea is, you have a big test suite, and you want to run it across a bunch of different machines all at once, so you can make it nice and fast, right? So instead of a test suite that runs for a couple hours, you run it across 20 nodes, and whatever 2 hours divided by 20 is, that's your new test runtime. So ABQ is great, but I don't want to talk about it today. What I want to talk about is a particular challenge that we ran into while we were implementing it. So we operate with this distributed model, right? We have like one server, you give us your test suite, you're like, okay, I want to run this across however many nodes, and we say, okay, all right, we'll take, oops, way too far. We say, okay, we'll take your test suite and run it across those nodes. All right, so as part of this, right, we need a server, and that's what I want to talk about today. We want this web server to have a high degree of concurrency because we wanted, to be able to handle many, many test suites at the same time and many, many workers for a single test suite. And we shipped ABQ as an open source piece of software, so we wanted the number of dependencies that we have to be quite low. So it's a single binary, you can deploy wherever you want, and we try to keep most of our dependencies in memory if possible. Okay, so time went on, we got more users, made a little bit of money. We're like, this is fantastic, this is great. People running more test suites, we're having a fun time. And then one day, one of our customers calls us, and they're like, hey, listen, you have a great product, but all of a sudden, we can't run any of our test suites. So I say, okay, what's the problem? So I open up my systemd journal, and my systemd journal tells me, well, okay, your thing is getting out of memory killed, so killed everywhere. And I was like, why is this happening? This sounds terrible. So I decided to run a synthetic test to try to reproduce this, and this is the kind of memory graphs that I got. So don't worry too much about the different colors here. The difference in colors is basically one line is memory with cache and one line is memory without. And the difference between these two graphs is the memory allocator used, and we'll get into that later. But the key point I want to make is the purple arrows here are when I started my test, and my test was I just ran a bunch of test suites against my server all at once and expected it to handle that workload. And the interesting point I want to make is the steady state here, right? So at this point, at 1700, our server entered a steady state where it wasn't doing any more work. We got no more requests or anything at all, and yet our baseline memory was very, very high, right? Around 70%. So the question is why? And you might be wondering what's happening over here, and the answer is that we hit an kill, and then the process got restarted. Okay, so this is what my face looks like. I was like, got to figure this out. So the natural conclusion is that we're leaking memory in our program somewhere, and we have to figure out why, right? So there's kind of two routes we can go. We can say, well, did we write bad software, and do we need to fix our application? Or we can say, is there something going on with our system dependency with our allocator? So of course, you never trust the latter idea first, because you're like, well, I write more bugs than my dependencies do. So we can think about that pretty easily. So we might ask, what are some things we want to check in our Rust application code to see if we're leaking memory somehow? So one immediate idea is, well, are we leaking pointers on the heap or something like this because we're breaking Rust memory invariants? If you're not using unsafe code, this is probably not going to happen to you, especially if you're depending on well-known libraries and the standard library. So it was pretty easy for us to just grab for unsafe. We didn't have any. Okay, that's probably not an issue. A very common source of memory leaks, I'm sure you know, is high and await data in some global variable that accumulates over time. Static memory in the static section of your program can be one example of this, but there are others that we'll see later on. That wasn't the case for us either. We checked the libraries that we were using. We just used the very popular ones in the ecosystem, so we didn't find any memory issues there. And the really nice thing about working in a language like Rust, or this is kind of a nice feature about C++, in my opinion, is the RAII model means that it's very easy for you to reason about the lifetime of your allocations, right? So especially if you have network requests that kind of map one-to-one with a single function. You can say, okay, well, I made this allocation in this request and this request handler, and so I know that the deallocation is going to happen roughly when that request completes. So if I know that my requests have typically take 5 milliseconds, well, I know how long my allocations are living for as well, right? Okay, so we didn't think it was any of these issues. There are some other things you might try to take a look at. You might say well, do you have a bunch of requests coming in at once that sort of blow your heap? The answer for us was maybe that's the case, but it doesn't explain the leak that we're seeing. You might check if there are unbounded connections that are growing, that are allocating more and more over time. This is sort of the same as having a global variable somewhere that just accumulates more and more. We didn't have this either. We checked if we allowed just unbounded message sizes. We don't. We hard cap the messages we receive at 1 megabyte. And something else that you might happen, especially when you're developing a server, right, is you launch your server at the top of your program, and even though the server doesn't have global variable in the sense that there's no variable that you declare static, you can still accumulate more and more data over time. But we knew that this wasn't the case because even though we do store some metadata with each test run, it's quite small, and we offload it over time. So really quickly, I want to give a shout out to Rust Analyzer for a great developer tool here. So the way that we found out this 1 kilobyte of metadata was we just hovered over our types and just chased some pointers and added them all up. And so great tool. Highly recommend if you haven't done this before. Okay, but the other thing you might notice is if you've seen what memory leaks in applications look like, they typically don't look like the graphs I showed you, right? There's typically slowly growing sawtooth kinds of curves, and that's not really what we're seeing here. Okay, so there's something a bit more interesting going on, and that brings me to the meat of the talk. I want to talk about the allocators that we use in our programs because process-wide global memory allocators are something that we all use, and I don't think we talk about them all that frequently. There's some talk these days, and there have been for the past few years about specialized allocator in certain regions of your program. Languages like Zig and stuff, and languages like those provide very fine-grained control of your allocator. But at least from me, I typically write a program, and I'm well, I just want someone to use it. I don't really care what allocator it has. Maybe I'll just choose one because someone said it was nice, but I don't really know what's going on. So before we get any further, you might be hearing the application problem that I described, and you might say, well, there's a lot of different ways that you can fix this, and I agree. So you might want to choose one specific allocator. You might want to use certain system calls directly. You might want to use specialized allocators like arenas, which are very popular when building web servers. Or you might even want to use a garbage collector. So all of these are really good options, and we'll get to them later. But first, I want to explore why memory allocation can be a problem in the first place. So the first point I want to make is how many of you are intimately familiar with malloc and free implementations? Okay, so a few hands, right? But I don't think this is something that especially application developers think about on a daily basis. So if I cast aside all my knowledge, maybe I studied malloc and free a couple of days in university, but if I take all that knowledge away and I just think about the interface that malloc and free expose, which is give me a chunk of bytes and take a chunk of bytes away from me, I might not think that this is a very complicated problem to solve, right? But it turns out that the memory allocators that we use in practice are very, very sophisticated. And lines of code might not be the best metric in general, but maybe it gives us a baseline to work with. So malloc ng, which comes from the musl libc implementation, is about 900 lines of code, which, okay, I think I can get why that needs to be the case. But then memalloc, which is developed by Microsoft, and Dan Lejeune, the Coca language also uses memalloc, is an order of magnitude more. And this, for me at least, this is immediately okay, there's something a lot more sophisticated going on than I can possibly understand from just the malloc and free interface that's exposed to me. And then JEmalloc, which is developed by Facebook, and TCmalloc, which is developed by Google, are a few times more than that as well, right? So the point here is that like clearly there's some knobs that we need to turn that are not immediately obvious to us in just the malloc and free interface. Okay, so I want to briefly go over a few reasons why memory allocators have a tough job to do. We won't get to all of them. Of course, we don't have enough time, and I hope it's not too boring if you already know some of these, but for the sake of extrapolating the reasons that we'll get to later. So the first very common reason that you might already know about is amortization, right? So maybe I'm an application and I'm like, well, I need some space for a vector because I have something I need to do. So I go to my allocator and I'm like, hey, can I please get some space for a vector? And the allocator says, you know, I would love to give you some space, but actually I don't have any memory free myself right now. So I need to go talk to the kernel, get that space for you, and then I'll give you back what you need. But, you know, talking to the kernel is usually pretty slow, at least relative to like how long it takes your code to call the allocator, right? Which is like a few instructions. And so the allocator might say, well, I know this is going to happen again at some point in the future, because if you're allocating now, you're probably going to allocate again. So let me go get a big slab of memory from the allocator, and then next time you ask me, I can just give you like a little piece from that slice rather than having to go talk again. So the allocator goes off, does this, it then has to do some bookkeeping to keep track of the other slab of memory that I can't give to you at this moment, and then says, all right, you can have this back, right? So the second time you call the allocator now is going to be much faster, but this is like already one source of complexity, right? It's just that we're trying to prevent expensive operations every time you call the allocator, so the allocator has to account for that in its implementation. These days, there are also like a bunch of interesting optimizations that allocators try to provide. So one that I'll mention here is this idea of size classes. The idea of size classes is like, suppose you have a bunch of variably sized allocations, like maybe you allocate 52 bytes and then follow that with a 56-byte allocation. Well, when's the next time you're going to allocate a 52-byte allocation? Like, probably not that often. So a lot of allocators try to round up to near sizes called size classes, and any allocation that like fits below the previous size class and next size class gets an allocation of the size of the next size class. And this makes certain things like memory fragmentation easier to manage. It also just helps the allocator with bookkeeping. There's some other reasons. Speaking of memory fragmentation, I'm sure we've all experienced this, but the idea with memory fragmentation, right, is like, suppose in this example that my yellow squares are my used allocations and my gray squares are my free allocations right now, or like free pieces of memory that I could hand out to incoming allocations. And suppose someone comes and they say, hey, I would like to allocate 128 bytes. And the allocator would say, oh, like, I would love to do that for you. Actually, I have 128 bytes free, but I can't give you the 128 bytes that I have free because it's not contiguous. And if you need a contiguous allocation, like, I just can't help you right now. And the downside of this is like, if you never have an allocation that fits within those 64-byte slots, then this is memory that your application isn't using but has gone to waste because it's staying in your application code and not released to the OS. Okay, so you might have also heard about free lists. Free lists are a caching mechanism that allocators use so that when you deallocate something, it gets put in a cache. And then when the next allocation comes in, it can go and check if there's a free slot in the free list rather than having to take a slower path either to the OS or like finding a bin with a certain size class. And another, like the final point I want to make is the context of allocators in multi-threaded programs, right? So if I'm designing an allocator and I want it to work efficiently on multi-threaded programs, I don't want all my threads talking to a single global allocator, because in programs that allocate a lot, this means you're going to have contention all the time, which isn't good. So a lot of high performance, high CPU performance allocators like give thread local allocators to each thread in your program, or try to share allocators between threads, and that's how they work. So I bring all this up to say, like, these are like non-trivial optimizations, and there's like some overhead with all of this, right? So like with size classes, you're giving up some amount of space. Maybe that space doesn't matter, but you're giving up some of it. It may not be obvious in your application that you're doing so. With like thread local allocators, well, it's clear that we have some fixed size overhead that we have to incur for each thread local allocator that we get. But also, if we have fragmentation inside of each thread local allocator, right, like that starts to accumulate over time. So there's some overhead with these optimizations, which can mean that you get degraded memory performance, or like degraded memory usage, even if you get increased CPU performance, right? Okay, so I want to like dive into a couple specific allocators because I think it's quite interesting, especially if you don't know some of the features they provide. So the first one I'd like to talk about is glibcs, which I think is probably the one that we're most familiar with, especially if we develop for Linux systems and use the default system allocator. So glibc provides these like thread local allocators to an extent that I mentioned. What they do is they create local allocators that are shared between one or more threads, and as contention increases, glibc will allocate more allocators to like split up between those threads, right? And they have like a thread local free list basically that you can use. But the interesting thing is that free doesn't give memory back to the OS in band. And this probably makes sense, right? Like if someone frees immediately, you don't want to be releasing to the OS every time. But the way that glibc does this is, as you free, glibc keeps track of the largest slab in memory, the largest like free unallocated slab it knows about, which it calls a top chunk. And glibc will only release memory back to the OS if that top chunk like grows to beyond a certain size. I forget what the size is exactly. But this is interesting, right? Because I think you and I can think of some examples where this might be a problem, right? If we have very, very heavy fragmentation, maybe it's the case that we never have a top chunk that's like large enough to be released, right? malloc-ng, which comes from the muscle libc, is quite different. So you may read online that muscle's malloc implementation is quite poor, which historically may have been the case, but in 2020, 2021, somewhere around that time, they re-implemented a new allocator, which is called malloc-ng. And malloc-ng is like specialized for low resource systems. So they try to release memory really, really actively. They don't have thread local allocators and things like this. But the interesting one I want to talk about is jmalloc. So I'm sure some of you use jmalloc in production. I know that I do for some applications. And jmalloc is a very, very sophisticated allocator, right? Like it does a lot of things to try to reduce fragmentation. Facebook obviously uses it in production. Like, this is not like a bad piece of software by any means. But there are a couple interesting options that I think may not be commonly known about, but are like very, very interesting when you dive deep into them. So the first one I'd like to bring up is an option that jmalloc exposes called cache oblivious. Cache oblivious is turned on by default. And what it does is it's a feature in jmalloc to try to more uniformly distribute your memory allocations. It's an option to try to more uniformly use the cache lines in your memory cache as you perform allocations, right? So we have this giant memory space, but our the L1 through L3 caches that we have in our computers are quite small. And so we want to try to make sure that the allocations that we have are best using the caches as best using the caches as possible, right? Because the CPU has some kind of mapping from a memory address to a cache line, and depending on the computer that you're using, the mapping algorithm can be quite different, right? So what jmalloc does is it says, okay, I don't know what the mapping algorithm is exactly, but I'm going to try to make sure that large allocations that I have map as uniformly as possible to all the cache lines as I could think would be the case. And how I'm going to do this is when I have a large allocation, I am going to place its starting memory address at a random offset within a memory page, right? So a memory page typically is 4 kilobytes on a Linux machine. So this can be great for your CPU efficiency, right? But the downside is that now if you have a 16 kilobyte allocation, unless you are very lucky and get the 1 out of 4,096 chance that it's right at the offset of a page, you need an extra page. You need an extra page for the buffer that accounts for the random offset, right? And you might think, well, okay, like, does this actually matter? And I would argue yes, because a lot of the popular crates, including standard libraries, say if you need to do an intensive if you need to do an I/O operation and allocate memory in the process for a buffer, you should allocate 8 kilobytes. But in the jemalloc land, that means you're probably allocating more than 8 kilobytes, right? Okay. So there's another option called decay-based purging. This is the default option for how jemalloc frees allocations. And by default, jemalloc will delay freeing a page to the OS for 10 seconds. Right? The idea here, again, is that like, oh, if your application comes back later and wants space to allocate something, well, you have a 10-second buffer before I release the page to the OS, and so things can become much faster from a CPU perspective. But the downside, I'm sure you can imagine, is like, again, you and I can think of cases where this might not be what you want. And if you're interested, there's an issue from the Cockroach DB implementers on the jemalloc repo discussing some of those implications. So the point I want to make is that, like when we use these general purpose allocators, right, and we don't know like in great detail what they might be doing, specifically in the context of our applications, we might run into some issues, right? Most of the time it's just fine, it's not an issue at all. But I think it's, at least in the communities that I run in, like I don't talk about this often, and I don't have a good sense of like when these kinds of issues can crop up, and then all of a sudden they do, and you have to figure out why. Okay, here's like a small chart showing some of the differences between the different allocators I talked about. I didn't dive into memmalloc's implementation, but if you're interested, there's like, there's a nice paper from Dan Lejeune that you can check out. So I think another interesting point here is that like all of these are general purpose allocators, and yet their like subset of features are somewhat different, right? So maybe that has something to say about like the efficacy of these optimizations in general for most programs, right? Like, certainly many programs benefit significantly from some of these optimizations, but maybe most programs don't. All right, so I want to touch quickly on like one implication of these kinds of things, specifically for the web server I was discussing at the beginning of the talk. Okay, so imagine we have 2 requests coming in to our web server. You can think of them as concurrent, but we'll see in a second that they are parallel. And in practice, the process block should be much larger, but I have to fit words into a slide. So let's say that the read, process, and write parts of this are asynchronous, and we're running on a multi-threaded async server, right? So these requests might in fact be processed in parallel if I have 2 threads that are each independently processing the request, right? But if I'm using Tokyo and I'm using the default work-stealing multi-threaded scheduler, what can happen is that like when I suspend one of the async operations, it can get stolen by another thread. And so we can end up in a situation where one of our requests starts on one thread and ends up on the other, right? And what does that mean for a lot of the like thread local optimizations that we were trying to do? It means that we lose out on some of that benefit, right? Because, well, now my deallocation at the end of my write, unfortunately, cannot just stay on the same thread that it was allocated on, because there are 2 different ones, right? And so, in particular for our case, there's many reasons that memmallok and glibc and jemalloc did not work for us. And if you're interested, you can ask me more in the end. But it turns out for us, like, we weren't getting any of these benefits because we had this multi-threaded async server. And so the overhead just like wasn't paying for itself. And we had a very low resource machine. And so we only had 1 gigabyte allocated for our machine, and like the overhead of jemalloc and memmallok just wasn't cutting it. We would blow our heap like as soon as we tried to do anything interesting. So we switched to malloc ng from memmallok, and things were just fine. As you can see, very different performance profile, and this is like with the same test in both cases, right? So very, very, very wide difference, and I think very interesting. And a final point I want to make is you'll notice, if you try to do this in your own programs, where you'll often notice is that if you increase the size, if you increase the memory on your machines to like 2 or 4 gigabytes or whatever, you'll get the exact same curve for like the meme alloc case, for example. So what we did for our customers when we first had this was we just like bumped them to 4 gigs, and we still had that fixed overhead at like whatever, 700 megabytes, but then like it didn't increase past that. Okay, so finally, I just want to touch on like a few things you might be thinking about and being like, oh, here's like a specific idea that I could do here. So you can certainly use specialized allocators, right? Maybe this is the most convenient with the language features that Rust provides today, but you can certainly use something like Bumpaloo to have, you know, I don't know, say like allocate like a nice 8 kilobyte slab for each of your requests, and when a request comes in, give it that 8 kilobyte slab, say, hey, you can do your work in here, and then at the end, just put it back into a list that you can give off to your next requests. If you have, like especially this producer-consumer pattern that doesn't work super great with with the allocators that I described here, you can try to use specialized allocators for like multi-threaded message passing type systems. So Microsoft's SNMalloc is one of those. And then, like from an application design perspective, try to avoid sharing between threads, of course. I think an interesting thing that maybe like I hadn't considered too much is like, well, okay, instead of having a multi-threaded async runtime, can I run multiple async runtimes on multiple threads? Maybe this is a bit trickier to get right in a web server world, but you could imagine how we do this, right? Like your request processing happens on a single thread. And another interesting idea is using scoped threads more often, right? So there, like, if you have a memory allocator that uses scoped memory pools, now you, like, maybe you can't think of this exactly, but you can kind of reason, okay, well, now I know roughly how long this like thread local allocator is going to live for with a scoped thread. And of course, some other things, right? We can try to more effectively use clone on write and try to use zero-cost deserialization. These might have some impact on the ergonomics of your program, but can be effective in these kinds of cases. So finally, if you run into these kinds of issues, what can you do? I think there's a bunch of different debug allocators that you can use and profilers. One thing I would mention, though, if you are using a profiler, you should be very careful. Because in these cases that I showed you, the profiler might show you what is being used and freed relative to your allocator. But it might not show you what is actually being used by your application relative to the OS. So you have to be quite careful here and choose the right one. And as I mentioned before, these libraries are very sophisticated and very complex. And JMalloc, I don't know, it has a giant man page. I can't even tell you how many options it has. But sometimes you need to play with this. And you might notice that I cross out GC here, and I think I do this just because I want to mention that I think like oftentimes we might think that memory allocators and garbage collectors are very different, but in fact, I think they solve exactly the same problem. It's mostly just a difference of like the language that consumes them, right? So typically in a GC, the user does not know the length of their allocations, and also like the user is willing to give the GC a lot of information about how their application works. And it just happens that those two parameters aren't the same for memory allocators, but what they need to do in terms of operations is quite similar. All right, so with that, I don't want to scare you. Obviously, your memory allocator probably doesn't matter. It's probably not the issue in your application, but sometimes it does matter, and so you should at least keep it in the back of your mind. And I think at the very least, like the easiest thing to do by far is just to try out a few different allocators and just choose the one with the best memory profile that doesn't hit your CPU. All right, thanks.